Tonight, we're going to embark on a journey into the deepest, most unsettling mystery of the cosmos. It's a mystery that challenges everything we thought we knew about the universe, about reality itself. Imagine looking at a familiar object, something you've seen countless times, and then realizing that 95% of it is invisible, intangible, and utterly unknown. That's essentially the situation we find ourselves in when we look at the universe. We thought we had a pretty good handle on things. We understood stars, galaxies, planets, and the fundamental particles that make them up. We could map the cosmos, trace its history, and even predict its future. But then, the evidence started piling up, slowly at first, then with an overwhelming force, suggesting that almost everything we observe is just a tiny, shimmering tip of an enormous, unseen iceberg. Most of the universe, it turns out, is missing. This isn't a speculative idea from science fiction. This is the stark, undeniable conclusion drawn from decades of meticulous astronomical observation and theoretical physics. Our universe is dominated by two enigmatic components: dark matter and dark energy. Together, these two entities make up about 95% of the entire cosmos. Ordinary matter, the stuff of stars, planets, gas, dust, and all life, including ourselves, accounts for a mere 5%. Think about that for a moment. 5%. Everything you have ever seen, touched, or experienced, every atom in your body, every star in the night sky, every galaxy stretching across billions of light years, all of it is just a tiny fraction of what's truly out there. The vast majority of reality operates beyond our senses, beyond our current understanding, a silent, invisible force shaping the destiny of everything we know. This isn't just a small gap in our knowledge, it's a gaping chasm. It means our cosmic inventory is profoundly incomplete. It means the very foundations of our physical laws, which work so perfectly on Earth and within our solar system, start to unravel on the grandest scales of the universe. It forces us to confront the possibility that our current understanding of gravity, of matter, of energy, might be fundamentally flawed or at least dramatically incomplete. This is a profound challenge, but also an exhilarating one. It's the ultimate scientific detective story, a quest to uncover the hidden components that dictate the universe's structure and evolution. Over the course of our journey tonight, we will delve deep into this cosmic inventory crisis. We will explore the compelling evidence that first hinted at these missing components, from the strange rotation of galaxies to the bending of light, our unseen mass. We will examine the leading candidates for what dark matter might be, the particles that could be passing through us right now, utterly undetectable by our current instruments. We will then turn our attention to dark energy, an even more bewildering force that is accelerating the expansion of the universe, pushing galaxies apart at an ever-increasing rate and determining the ultimate fate of all things. We'll look at the experiments and observations that are pushing the boundaries of our knowledge, the massive telescopes and underground laboratories searching for answers. And finally, we will contemplate the profound implications of this missing universe for our place in the cosmos, for the future of humanity, and for the very nature of reality. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive into the unseen. Let's begin by grounding ourselves in what we do know, the tiny fraction of the universe that is directly observable and comprehensible, the visible universe. This is the realm of ordinary, or baryonic, matter. It's the stuff composed of protons, neutrons, and electrons, forming atoms, which in turn form molecules, and ultimately, everything we interact with. Our understanding of this visible universe is one of humanity's greatest intellectual triumphs. We've meticulously catalogued the elements, from hydrogen to oganesson, and understood their properties through the elegant framework of the periodic table. We've unraveled the laws of electromagnetism, explaining how light interacts with matter, how chemical bonds form, and how energy is generated and transmitted. We've developed theories of gravity that accurately describe the motion of planets, the formation of stars, and the dynamics of galaxies. The most prominent features of the visible universe are, of course, the stars. These colossal balls of plasma are the universe's natural nuclear furnaces, fusing lighter elements into heavier ones and releasing immense amounts of energy in the process. We understand their life cycles with remarkable detail, how they form from collapsing clouds of gas and dust, spend millions or billions of years in a stable phase like our Sun, and then evolve into red giants, white dwarfs, neutron stars, or even black holes, depending on their initial mass. Each stage of a star's life is characterized by distinct physical processes, temperatures, pressures, and compositions, all governed by the well-understood laws of nuclear physics and thermodynamics. The light they emit, analyzed through, we have mapped billions of stars in our own Milky Way galaxy and countless more in distant galaxies, creating an intricate celestial atlas. Beyond stars, we have planets, moons, asteroids, and comets, the diverse array of celestial bodies that populate planetary systems. Our own solar system, with its 8 major planets and numerous dwarf planets, has been explored by an armada of robotic probes, revealing a breathtaking diversity of landscapes, atmospheres, and geological processes. From the scorching, cratered surface of Mercury to the icy, methane-laced lakes of Titan, we've gathered an astonishing amount of data about these worlds, allowing us to understand their formation, evolution, and potential for harboring life. We've even begun to detect and characterize thousands of exoplanets orbiting other stars, expanding our understanding of planetary systems beyond our own. Then there are the vast stretches of interstellar and intergalactic space, filled with tenuous clouds of gas and dust. These nebulae, often beautifully illuminated by nearby stars, are the nurseries where new stars are born, cycling matter back into the cosmic ecosystem. We can observe these clouds in various wavelengths, from radio waves that penetrate obscuring dust to infrared radiation emitted by warm gas, revealing their intricate structures and dynamic processes. These seemingly empty spaces are, in fact, teeming with diffuse matter, the raw ingredients for future cosmic structures. All these component stars, planets, gas, dust are organized into larger structures. Galaxies. Our Milky Way is a majestic spiral galaxy, a cosmic island containing hundreds of billions of stars, along with vast quantities of gas and dust, all bound together by gravity. We understand the basic principles of galaxy formation, how primordial density fluctuations in the early universe led to the gravitational collapse of matter, forming the first proto-galaxies, which then merged and grew into the grand structures we see today. Galaxies themselves are not isolated, they cluster together, forming groups and superclusters, which are in turn connected by vast filaments of matter, creating what astronomers call the cosmic web, a sponge-like arrangement of matter. On the largest scales, interspersed with enormous empty voids, the success of atomic physics and chemistry in explaining the composition and behavior of all this visible matter is truly remarkable. The Standard Model of particle physics, though it primarily deals with subatomic particles and forces, provides the bedrock for understanding how protons, neutrons, and electrons interact to form atoms, and how those atoms then interact to form everything else. We can explain why the sun shines, why planets are rocky or gaseous, why nebulae glow, and why galaxies hold together, all using the same fundamental laws that govern experiments in laboratories on Earth. However, there's a crucial limitation to this visible universe. We can only see what emits or reflects electromagnetic radiation, that is, light, radio waves, X-rays, gamma rays, and so on. Anything that doesn't interact with light remains invisible to our telescopes. For centuries, the implicit assumption was that what we could see was essentially all there was. If a celestial object didn't shine, it was either too small, too dim, or simply not there in significant quantities. This assumption, deeply ingrained in our scientific worldview, was about to be shattered by a series of unsettling observations that began to emerge from the shadows of the cosmos. The universe, it turned out, was playing a very sophisticated game of hide-and-seek, and most of its mass was winning. The first whispers of the universe's missing mass emerged not from the elegant equations of theoretical physics, but from the painstaking observations of astronomers peering through their telescopes. The initial clues were subtle, anomalies in the gravitational behavior of celestial objects that simply couldn't be explained by the visible matter alone. These discrepancies began to accumulate, forming a compelling case for something unseen, something profound, that was exerting a powerful gravitational influence on the cosmos. One of the earliest and most significant observations came from Swiss-American astronomer Fritz Zwicky in the 1930s. Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies located hundreds of millions of light-years away. He meticulously measured the velocities of individual galaxies within this cluster. By applying the virial theorem, a formula that relates the kinetic energy of a system to its potential energy, he could estimate the total mass required to keep the cluster gravitationally bound. If the galaxies were moving too fast, the cluster should simply fly apart, dispersing its members into the vast emptiness of intergalactic space. But the Coma Cluster was clearly stable, a densely populated gravitational island in the cosmos. Zwicky's calculations revealed a startling discrepancy. The visible mass of the galaxies in the Coma Cluster, derived from their luminosity, was far too small to account for their observed speeds and the cluster's stability. He estimated that the cluster contained about 400 times more mass than was visually observable. To explain this missing mass, Zwicky proposed the existence of an invisible, undetectable substance that he called Dunkelmaterie, or dark matter. His findings were revolutionary, suggesting that a significant portion of the universe's mass was hidden from view. However, Zwicky's ideas were ahead of their time and were largely met with skepticism, remaining unexplored for decades. Decades later, in the 1970s, the concept of dark matter gained renewed and much stronger traction, thanks to the groundbreaking work of American astronomer Vera Rubin and her colleague Kent Ford. Rubin was studying the rotation curves of spiral galaxies, beginning with the Andromeda Galaxy, our closest large galactic neighbor. A galaxy's rotation curve plots the orbital speed of stars or gas against their distance from the galaxy's center. According to Newtonian gravity, if most of a galaxy's mass were concentrated in its luminous central bulge, then stars in the outer regions should orbit progressively slower, much like planets farther from the Sun in our solar system. However, Rubin and Ford's observations showed something entirely different. They found that stars and gas clouds on the outer edges of spiral galaxies were orbiting at roughly the same speed as those closer to the center, or even faster. The rotation curves were remarkably flat, extending far beyond the visible edge of the galaxies. This meant that the gravitational pull holding these outer stars in their orbits was far greater than what could be accounted for by the visible stars, gas, and dust alone. If only visible matter were present, these rapidly moving outer stars should have been flung out into intergalactic space, causing the galaxies to literally tear themselves apart. Yet, galaxies remained intact, spinning majestically across the cosmos. Rubin's meticulous and extensive observations provided compelling, independent evidence for the existence of a massive, invisible halo of matter surrounding galaxies. This invisible matter, which exerted a powerful gravitational pull but did not emit or absorb light, was precisely what Zwicky had called dark matter. Rubin's discoveries were so persuasive that the scientific community began to seriously consider and embrace the concept of dark matter. Her work, confirmed by subsequent observations, showed that spiral galaxies must contain at least 5 to 10 times more mass than could be directly observed. The evidence for dark matter continued to mount from other phenomena. One of the most visually stunning and undeniable proofs came from the study of gravitational lensing. Einstein's theory of general relativity predicts that massive objects warp the fabric of spacetime around them, and this curvature causes light from distant sources to bend as it passes by. This phenomenon, known as gravitational lensing, can act like a cosmic magnifying glass, distorting and amplifying the images of background galaxies. The degree of distortion is directly proportional to the amount of mass present, regardless of whether that mass is visible or not. The ultimate smoking gun for dark matter came from observations of the Bullet Cluster, formerly known as 1E65756. This remarkable object is the result of a colossal collision between two galaxy clusters that occurred about 3.8 billion light-years from Earth. When these two clusters smashed into each other, their constituent components behaved differently. The ordinary matter, primarily in the form of hot, X-ray emitting gas, collided and slowed down due to electromagnetic interactions, forming a pink-hued cloud detected by the Chandra X-ray Observatory. However, gravitational lensing studies of the Bullet Cluster revealed that the bulk of the mass in the system, represented in blue in composite images, had passed straight through the collision largely undisturbed. This mass distribution was clearly offset from the hot, X-ray emitting gas. The visible galaxies, composed of ordinary matter, also mostly passed through without significant interaction, much like the invisible mass. This striking separation of ordinary, interacting gas from the main gravitational mass provided powerful direct evidence that most of the mass in the cluster was not ordinary matter, but rather a collisionless, non-interacting substance. Dark matter, being collisionless, simply sailed through the interaction, while the ordinary gas was slowed and heated. This observation was incredibly difficult to explain without the presence of dark matter, and presented a significant challenge to alternative theories that sought to explain the anomalies by modifying gravity alone. Further evidence for dark matter came from the study of the large-scale structure of the universe. Cosmological simulations showed that the cosmic web of galaxies and galaxy clusters could only form if there was a substantial amount of cold dark matter providing the gravitational scaffolding for ordinary matter to clump around. Without dark matter, the visible matter would not have had enough gravitational pull to form the complex structures we observe today within the age of the universe. The temperature distribution of hot gas in galaxies and clusters, as well as the subtle anisotropies in the cosmic microwave background radiation, also align perfectly with a universe containing a dominant component of dark matter. These lines of evidence, accumulated over decades and observed across various cosmic scales, painted a consistent and undeniable picture. There is a huge amount of invisible mass in the universe that we cannot see, but whose gravitational influence is pervasive and profound. The initial clues, first noted by Zwicky and then compellingly demonstrated by Rubin, evolved into a scientific consensus, firmly establishing dark matter as an essential, albeit mysterious, component of our universe. The question then shifted from does it exist to what is it? With the compelling evidence for its existence firmly established, the scientific community turned its attention to the even more challenging question: what exactly is dark matter? This invisible substance, which makes up about 27% of the universe's total mass energy content, doesn't emit, absorb, or reflect light, making it extraordinarily difficult to study. It interacts with ordinary matter primarily through gravity, and possibly through the weak nuclear force, but not through electromagnetism or the strong nuclear force. This unique set of properties immediately rules out many conventional forms of matter. First, let's clarify what dark matter is not. It is not simply ordinary baryonic matter that is too dim to see. Baryonic matter, made of protons and neutrons, interacts with light, even if it were in the form of very dim stars, brown dwarfs, failed stars, or vast clouds of non-luminous gas. There are several reasons why these options have been largely ruled out. The abundance of baryonic matter in the universe is tightly constrained by observations of the cosmic microwave background and Big Bang nucleosynthesis, the process that formed the first light elements in the early universe. These observations show that baryonic matter can only account for about 5% of the universe's total mass energy. This means that if dark matter were baryonic, the numbers simply wouldn't add up. Furthermore, Large astronomical surveys looking for MOCHOs, massive astrophysical compact halo objects, which include hypothetical dim objects like brown dwarfs or rogue planets, have largely come up empty. These surveys would use microlensing, observing the temporary brightening of a distant star as a MOCHO passes in front of it, and gravitationally lenses its light. While some microlensing events have been observed, they are not nearly frequent enough to account for the vast amount of dark matter required. Black holes, another form of very dense, non-luminous baryonic matter, are also not thought to be the primary component of dark matter. While supermassive black holes reside at the centers of galaxies, and stellar mass black holes are the remnants of massive stars, their total mass contribution is far too small, and their gravitational lensing signatures would be different from what we observe from dark matter halos. So, if dark matter isn't ordinary matter, it must be something entirely new, a type of exotic particle not included in the standard model of particle physics. This is where the search becomes a true frontier of scientific discovery. Intertwining cosmology with particle physics, scientists have proposed several candidate particles for dark matter, each with its own theoretical underpinnings and experimental challenges. The leading candidate for decades has been the WIMP, or weakly interacting massive particle. WIMPs are hypothetical particles that are much heavier than protons, perhaps tens to thousands of times the mass of a proton. As their name suggests, they are thought to interact very weakly with ordinary matter, primarily through gravity and possibly the weak nuclear force. This weak interaction explains why they are so difficult to detect, and why they pass through ordinary matter almost. WIMPs are considered cold dark matter because they would have been moving relatively slowly in the early universe, allowing them to clump together and form the gravitational seeds for galaxies and large-scale structures. This cold dark matter model CDM successfully explains the formation of the cosmic web and the distribution of galaxies we observe. Another class of candidates is axions. These are much lighter particles than WIMPs, perhaps billions of times lighter than an electron, and they are also thought to interact very weakly with ordinary matter. Axions were originally proposed to solve a different problem in particle physics, related to the strong nuclear force, but they naturally emerged as a dark matter candidate. Their extremely low mass and weak interaction make them even more elusive than WIMPs. Sterile neutrinos are another theoretical possibility. Unlike the three known types of neutrinos, which interact through the weak nuclear force, sterile neutrinos would not interact with any of the fundamental forces except gravity. This makes them sterile to the standard model forces. They could have a small mass, making them a warm dark matter candidate, meaning they would have moved faster than cold dark matter in the early universe. However, current observations of large-scale structure tend to favor cold dark matter, which clumps more efficiently. The search for these elusive dark matter particles is a monumental undertaking, involving a global network of experiments employing various detection strategies. These searches can be broadly categorized into three main types: direct detection, indirect detection, and collider searches. Direct detection experiments aim to directly observe a dark matter particle colliding with an atomic nucleus in a highly sensitive detector. These experiments are typically located deep underground, often in old mines, to shield them from cosmic rays and other background radiation that could mimic a dark matter signal. Detectors are filled with supercooled materials, such as liquid xenon used in experiments like xenons and Lux Zeppelin, or germanium, used in experiments like CDMS. The idea is that if a WIMP passes through the detector and occasionally collides with an atomic nucleus, it would impart a tiny amount of energy, creating a faint flash of light or a measurable vibration. These signals would be extremely rare, perhaps only a few events per year in a large detector, hence the need for extreme sensitivity and shielding. Despite decades of searching and increasingly sensitive detectors, direct detection experiments have so far yielded no results, meaning no definitive WIMP signal has been observed. This has led to increasingly tighter constraints on the mass and interaction strength of WIMPs. pushing the search into new, unexplored parameter spaces. Indirect detection experiments look for the products of dark matter annihilation or decay. If dark matter particles are their own antiparticles, or if they decay into standard model particles, they could produce high-energy photons, gamma rays, neutrinos, or cosmic rays. Telescopes like NASA's Fermi Gamma Ray Space Telescope, the EMSO-2 experiment on the International Space Station, and ground-based neutrino observatories like IceCube search for these telltale signatures in regions where dark matter is expected to be abundant, such as the center of our Milky Way galaxy or in dwarf galaxies. While some tantalizing hints have emerged, such as an excess of gamma rays from the galactic center, these signals are often difficult to definitively attribute to dark matter and could have other astrophysical explanations. More work is needed to rule out less exotic explanations. Collider searches, such as those conducted at the Large Hadron Collider (LHC) at CERN, try to produce dark matter particles in high-energy collisions. If dark matter particles are indeed new fundamental particles, they might be created when ordinary particles are smashed together at extreme energies. Since dark matter particles would not interact with the detectors, their presence would be inferred by missing energy, a deficit in the total energy, measured after a collision, carried away by the undetected dark matter particles. The LHC has placed constraints on the continued absence of a direct detection of dark matter particles has led to a re-evaluation of some of the leading candidates and a renewed exploration of alternative theories. Some physicists are exploring more exotic dark matter models, such as self-interacting dark matter, where dark matter particles interact with each other in ways that visible matter does not. Others are considering fuzzy dark matter, composed of extremely light particles that behave more like waves than particles on galactic scales. The dark matter problem remains one of the most significant puzzles in fundamental physics, a testament to the universe's capacity to surprise us and push the boundaries of our understanding. The search continues, driven by the profound realization that a vast, invisible ocean of matter surrounds us, subtly shaping the cosmos, and waiting to reveal its true nature. As if the mystery of dark matter weren't enough, the universe had another, even more unsettling surprise in store. Dark energy. This enigmatic force, discovered much more recently than dark matter, is responsible for the accelerating expansion of the universe, a phenomenon that completely overturned our previous understanding of cosmic evolution. Its emergence is a story of unexpected observations, a re-evaluation of an old idea, and a profound shift in our cosmological paradigm. To understand dark energy, we first need to revisit the concept of the expanding universe. In the 1920s, Edwin Hubble made the groundbreaking discovery that galaxies are receding from us, and the farther away a galaxy is, the faster it is moving away. This phenomenon, known as Hubble's law, provided the first observational evidence for an expanding universe, a universe that began with a Big Bang and has been growing ever since. The expansion was initially thought to be slowing down due to the gravitational pull of all the matter within it, much like a ball thrown upwards slows under Earth's gravity. Cosmologists debated whether the universe contained enough matter to eventually halt its expansion and cause it to collapse in a big crunch, or if it would expand forever, gradually fading into a big freeze or heat death. Enter Albert Einstein and his greatest blunder. When Einstein formulated his theory of general relativity in the early 20th century, his equations predicted a dynamic, expanding or contracting universe. At the time, the prevailing view was that the universe was static. To reconcile his equations with this belief, Einstein introduced a term called the cosmological constant, represented by the Greek letter lambda, into his equations. This constant acted as a repulsive force, counteracting gravity and allowing for a static universe. When Hubble discovered the expanding universe, Einstein famously called the cosmological constant his greatest blunder, for artificially forcing a static solution when his equations had already predicted expansion. He removed the term, and it largely faded into obscurity. However, The cosmological constant was destined for a spectacular ray emergence. The key to its return lay in precisely measuring the rate of the universe's expansion over cosmic history. To do this, astronomers needed standard candles objects with a known intrinsic brightness that could be used to measure distances across the vastness of space. The most reliable cosmic standard candles turned out to be Type Ia supernovae. Type Ia supernovae are incredibly powerful and consistent stellar explosions. They occur in binary star systems where a white dwarf star, the dense remnant of a sun-like star, siphons matter from a companion star. When the white dwarf accumulates enough mass to reach a critical limit, known as the Chandrasekhar limit, about 1.4 times the mass of our Sun, it becomes unstable and undergoes a thermonuclear runaway, exploding with a brilliance that can briefly outshine an entire galaxy. Crucially, because they explode at a consistent mass, Type Ia supernovae all reach roughly the same peak luminosity. By comparing their observed apparent brightness with their known intrinsic brightness, astronomers can calculate their distance from Earth with remarkable accuracy. In the late 1990s, two independent teams of astronomers embarked on a mission to measure the universe's expansion rate using these Type Ia supernovae. The Supernova Cosmology Project, led by Saul Perlmutter, and the Heisey Supernova Search Team, led by Brian Schmidt and Adam Rees, meticulously observed dozens of distant Type Ia supernovae. Their goal was to determine if the universe's expansion was indeed slowing down, as gravity dictated. The results, announced almost simultaneously in 1998, were nothing short of revolutionary and completely unexpected. Both teams found that the distant supernovae were dimmer than they should have been. If the universe's expansion was decelerating, this dimness implied that the supernovae were farther away than predicted, meaning the universe had expanded more than expected. During the time their light had been traveling towards us, the only way for this to happen was if the expansion of the universe was not slowing down, but rather speeding up. The universe's expansion was accelerating. This discovery sent shockwaves through the scientific community. It earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011 and fundamentally reshaped our understanding of the cosmos. It was as if a ball thrown upwards was not only failing to slow down, but was suddenly gaining speed, accelerating away from Earth. This implied the existence of a mysterious, repulsive force acting on the largest scales of the universe, counteracting gravity and pushing galaxies apart. This enigmatic force was dubbed dark energy. The ray emergence of Einstein's cosmological constant, once considered his greatest blunder, suddenly seemed like a stroke of prescience. It was the simplest theoretical explanation for this accelerating expansion: a uniform energy density inherent to space itself, a constant repulsive force that doesn't dilute as the universe expands. The universe's ultimate fate, once thought to be a battle between gravity and initial expansion, now had a new, powerful player. Dark energy had made its unsettling debut, revealing that the universe was not only filled with invisible matter, but was also being driven apart by an unknown, pervasive energy. Just as with dark matter, the discovery of dark energy immediately led to the profound question: what exactly is it? This mysterious force, which constitutes roughly 68% of the universe's total mass energy content, is even more perplexing than dark matter. While dark matter is a form of matter that interacts gravitationally, dark energy is something else entirely, a form of energy that exerts a repulsive gravitational force, causing the universe's expansion to accelerate. To begin, let's clarify what dark energy is not. It is not dark matter. Dark matter clumps together gravitationally, forming halos around galaxies and influencing the formation of cosmic structures. Dark energy, on the other hand, appears to be smoothly distributed throughout space, acting uniformly and exerting its repulsive force everywhere. It doesn't cluster, it permeates. The leading candidate for dark energy is, surprisingly, Einstein's cosmological constant. This idea posits that dark energy is an intrinsic property of space itself, a fundamental energy density of the vacuum. As space expands, more vacuum comes into existence, and therefore, more dark energy appears, maintaining a constant energy density. This constant energy density would naturally lead to an accelerating expansion, as its repulsive effect would not dilute over time. However, there's a monumental problem with this elegant solution, a problem so severe that it's often called the worst prediction in physics. Quantum field theory, our best theory for describing the behavior of particles and forces, predicts that the vacuum of space should be teeming with virtual particles constantly popping in and out of existence. These virtual particles would contribute to the vacuum energy, and thus to the cosmological constant. When physicists try to calculate the expected value of this vacuum energy, they arrive at a number that is an astounding 10,120, or 1 followed by 120 zeros, times larger than the observed value of dark energy. This is an unfathomably huge discrepancy, suggesting that either our understanding of quantum mechanics is profoundly incomplete when applied to cosmology, or there's some unknown mechanism that cancels out almost all of this vacuum energy, leaving behind only the tiny amount we observe as dark energy. This vast difference between theoretical prediction and observation remains one of the greatest unsolved puzzles in all of science. Given this enormous theoretical hurdle, other explanations for dark energy have been proposed. One alternative is quintessence, a hypothetical dynamic energy field that changes over time and space. Unlike the cosmological constant, which is truly constant, quintessence would be a scalar field that evolves, meaning its strength and density could vary throughout cosmic history. This would make the acceleration of the universe not necessarily constant, but possibly changing. Such a field would be similar to the inflated field hypothesized to drive the rapid expansion during the very early universe cosmic inflation. However, like WIMPs for dark matter, quintessence requires the existence of new particles and forces that have not yet been observed. Another class of alternative explanations involves modifying Einstein's theory of general relativity on cosmic scales. Perhaps gravity itself behaves differently over the vast distances and low densities of the universe than it does in our solar system or around black holes. Theories like gravity propose alterations to the gravitational equations, attempting to explain the accelerating expansion without invoking a new, mysterious energy component. While these modified gravity theories can sometimes reproduce the observed cosmic acceleration, they often face challenges in explaining other phenomena or in remaining consistent with local tests of gravity. The nature of dark energy has profound implications for the ultimate fate of the universe. If dark energy is indeed a cosmological constant, meaning its density remains constant as space expands, then the universe will continue to accelerate its expansion indefinitely. Galaxies will recede from each other at an ever-increasing rate, eventually becoming so distant that their light will never reach us. Eventually, even individual galaxies will be torn apart by the expansion, and eventually, even atoms themselves could be ripped asunder in a Big Rip scenario. If dark energy grows stronger over time, however, with a constant dark energy, the most likely fate is a big freeze or heat death, where the universe expands, cools, and becomes increasingly dilute, with all stars eventually burning out and all matter decaying, leaving behind a cold, dark, empty void. The Big Crunch scenario, where the universe eventually collapses back on itself, is largely ruled out by current observations, as dark energy's repulsive force is too dominant. Astronomers use several observational probes to study dark energy and constrain its properties. The cosmic microwave backgrounds, CMBs, the faint afterglow of the Big Bang, a relic radiation from when the universe was only about 380,000 years old. The subtle temperature fluctuations, anisotropies, in the CMB provide a snapshot of the early universe's composition and geometry. By analyzing these patterns, cosmologists can infer the total amount of matter and energy in the universe, including the proportions of ordinary matter, dark matter, and dark energy. The CMB data strongly supports a universe that is geometrically flat and dominated by dark energy, confirming the accelerating expansion. Baryon acoustic oscillations (BAO) act as another standard ruler in the early universe, before matter and radiation decoupled. Sound waves propagated through the hot, dense plasma. These sound waves left characteristic imprints on the distribution of matter, creating slight overdensities at a specific length scale. As the universe expanded, this ruler stretched with it. By observing the clustering of galaxies at different distances and identifying this characteristic BAO scale, astronomers can measure the expansion history of the universe and, consequently, the influence of dark energy over time. Large-scale galaxy surveys also provide crucial data. By mapping the distribution of galaxies across vast cosmic volumes, astronomers can study how gravity has shaped structures over billions of years. Dark energy's repulsive force affects the growth of these structures, making them less dense than they would be in a universe dominated solely by gravity. These surveys help to constrain the equation of state of dark energy, a measure of how its pressure relates to its density, which can distinguish between a cosmological constant and other dynamic dark energy models, like quintessence. Despite these sophisticated observational techniques, the true nature of dark energy remains one of the most profound enigmas in science. It is a force that dictates the ultimate fate of the universe, yet we have no fundamental understanding of what it is or why it has the precise value it does. The search for its true identity continues to drive cutting-edge research in both astronomy and particle physics, pushing the boundaries of our knowledge and forcing us to reconsider the very nature of space, time, and energy. The mysteries of dark matter and dark energy, once isolated anomalies, have now been woven into the very fabric of our standard cosmological model. This model, known as Lambda CDM, stands as the most successful framework for describing the universe from its earliest moments to its ultimate fate. CDM incorporates both a cosmological constant lambda to account for dark energy and cold dark matter CDM to explain the invisible mass. It's a testament to decades of scientific inquiry, bringing together disparate observations into a surprisingly coherent picture. Even if some of its core components remain unknown, the CDM model posits that the universe is composed of approximately 5% ordinary baryonic matter, 27% cold dark matter, and 68% dark energy. This precise cosmic inventory, derived from numerous independent observations, allows the model to successfully explain a wide range of cosmological phenomena. One of the model's greatest triumphs is its ability to explain the subtle anisotropies, or temperature fluctuations, in the cosmic microwave background CMB. The CMB, as we discussed, is the afterglow of the Big Bang. Its patterns are incredibly sensitive to the universe's composition and geometry. The CDM model, with its specific proportions of dark matter and dark energy, accurately predicts the observed peaks and troughs in the CMB power spectrum, confirming that the universe is spatially flat and dominated by these invisible components. The CDM model also provides a robust explanation for the formation of large-scale structure in the universe. In the early universe, tiny quantum fluctuations in the density of matter were amplified by gravity. Cold dark matter, being non-interacting and much more abundant than baryonic matter, was able to clump together much earlier and more efficiently. These dark matter clumps acted as gravitational seeds, or scaffolding around which ordinary matter subsequently gathered. Without dark matter, ordinary matter would not have had enough time to form the complex cosmic web of galaxies, galaxy clusters, and superclusters that we observe today. The CDM model, when run in supercomputer simulations, beautifully reproduces the intricate filamentary structures and voids of the cosmic web, matching observational data with remarkable precision. The cosmic web itself is a breathtaking visualization of this underlying structure. Imagine vast, interconnected filaments of dark matter stretching across billions of light-years, forming a cosmic skeleton. At the intersections of these filaments are massive nodes, where galaxy clusters reside. Along the filaments themselves, galaxies are strung like pearls on a necklace. In between these structures are enormous, relatively empty voids, regions where matter is sparse. This intricate, sponge-like structure is entirely dictated by the gravitational influence of dark matter, with ordinary matter merely tracing its outlines. Furthermore, the CDM model successfully explains the accelerating expansion of the universe, with dark energy providing the repulsive force that drives galaxies apart. At an ever-increasing rate, it reconciles Hubble's initial discovery of expansion with the later, more precise measurements that revealed its acceleration. The model predicts the universe's expansion history, from its early inflationary phase to its current accelerating state, and offers insights into its ultimate fate. Despite its phenomenal successes, the CDM model is not without its limitations. Its greatest weakness lies in the fact that its two dominant components, dark matter and dark energy, remain fundamentally mysterious. We don't know what dark matter particles are, and we don't understand the true nature of dark energy or why it has the precise value it does. These aren't minor details, they represent 95% of the universe's mass energy content. This means that while the CDM model is an incredibly effective description of the universe, it's not a complete explanation. It tells us what is happening and how much of these mysterious components there are, but not why they exist or what they truly are. This tension between the model's observational success and the CDM model is the best framework we have, a powerful tool for understanding the universe, but it also points directly to the need for new physics, beyond the standard model of particle physics, and perhaps even beyond Einstein's general relativity. It's a reminder that our journey of discovery is far from over, and the most profound secrets of the cosmos still lie hidden in the missing 95%. The profound implications of a universe dominated by dark matter and dark energy extend far beyond the realm of academic cosmology. They touch upon our philosophical understanding of reality, push the boundaries of technological innovation, and guide the search for a unified theory of everything. The fact that 95% of the cosmos is invisible and unknown forces us to confront a deep humility in the face of the universe's complexity. Philosophically, the missing universe shatters any lingering anthropocentric notions we might hold. For centuries, humanity placed itself at the center of the cosmos, then at the center of the solar system, then in a typical galaxy. Now we realize that even the very matter we are made of is a cosmic rarity. We are composed of a mere 5% of the universe's substance, making us truly peripheral in terms of cosmic inventory. This realization is both humbling and strangely liberating. It means the universe is far stranger, far more diverse, and far more expansive in its possibilities than we ever dared to imagine. Our limited senses and instruments reveal only a sliver of reality, suggesting that there might be entire realms of existence operating just beyond our perception, influencing everything around us without ever directly interacting. Technologically, the quest to understand dark matter and dark energy is driving unprecedented advancements. The search for dark matter particles, for instance, has led to the development of incredibly sensitive detectors, buried deep underground and shielded from all known interference, capable of detecting the faintest whisper of an interaction. These experiments, like Xenon's, Lux Zeppelin, and Pandax, are pushing the limits of ultra-low background physics, inspiring innovations in cryogenics, material science, and signal processing. Future generations of these detectors will be even larger and more sensitive, aiming to finally catch that elusive dark matter particle. The study of dark energy, on the other hand, is fueling the construction of massive new telescopes and observational facilities. Projects like the Euclid Space Telescope, NASA's Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory, formerly LSST, are designed to map billions of galaxies across vast cosmic volumes, precisely measuring their distances and distributions. By observing gravitational lensing effects, baryon acoustic oscillations, and the evolution of galaxy clusters with unprecedented detail, these observatories will gather the data needed to constrain the properties of dark energy, distinguish between different theoretical models, and potentially reveal whether it is truly a constant or an evolving field. Furthermore, the burgeoning field of gravitational wave astronomy, pioneered by detectors like LIGO and Virgo, might offer entirely new ways to probe the universe's dark components. Though the connection is still in its early stages of exploration, the existence of dark matter and dark energy also serves as a powerful beacon guiding the search for a unified theory of fundamental forces. The standard model of particle physics, while incredibly successful, does not include gravity and offers no explanation for dark matter or dark energy. This suggests that there is new physics beyond the standard model waiting to be discovered. Theorists are exploring various avenues, such as supersymmetry, which predicts that every known particle has a heavier superpartner, some of which could be dark matter candidates, string theory and M theory, which propose that fundamental particles are not point-like but tiny vibrating strings, or membranes in higher dimensions, might also offer frameworks for incorporating dark matter and dark energy into a more complete description of reality. Some theories even suggest that dark matter might have its own dark forces and dark photons, forming a hidden sector of the universe that interacts only gravitationally with our visible world. The ultimate goal is to connect these mysteries to this quest for a unified theory. A theory of everything is the holy grail of modern physics, and the missing universe provides the most compelling motivation for its pursuit. It forces us to ask whether our understanding of gravity itself needs to be modified on cosmic scales, or if there truly are new particles and fields that constitute the vast majority of existence. The journey of discovery is far from over. Each new observation, each null result from a dark matter detector, each refinement in our cosmological models, brings us closer to understanding the true nature of the universe. It's a testament to human curiosity and ingenuity, a relentless pursuit of knowledge that pushes the very limits of our intellectual capacity. The implications are profound. The universe is not what it seems, and the majority of reality is still hidden from our view. But in that very mystery lies the greatest adventure of all, a scientific quest that promises to redefine our place in the cosmos and reshape our understanding of what is possible. The future of discovery is dark, in the most exciting and profound sense of the word. As we bring our cosmic journey to a close tonight, let's reflect on the profound realization that most of the universe is missing. We began by grounding ourselves in the familiar, the radiant 5% of the cosmos made of ordinary matter, the stars, planets, and galaxies that light up the night sky. But we quickly ventured into the unseen, guided by the gravitational anomalies that first hinted at a hidden reality. We learned about Fritz Zwicky's early, prescient observations in the 1930s, when he noticed that galaxies in the Coma cluster were moving too fast to be held together by their visible mass alone. His introduction of Dunkel Materie was a revolutionary, if initially ignored, idea. Decades later, Vera Rubin's meticulous work on galaxy rotation curves provided compelling, independent evidence, showing that stars on the outer edges of spiral galaxies were orbiting far too quickly, implying a vast, invisible halo of matter extending far beyond the luminous regions. And then came the definitive smoking gun, the Bullet cluster, where gravitational lensing clearly showed a separation between ordinary, interacting gas and the bulk of the mass, which passed through undisturbed, confirming dark matter's collisionless nature. Dark matter, we understand, is not ordinary matter. It's an exotic, unknown substance that makes up about 27% of the universe, interacting primarily through gravity. The search for its constituent particles continues in deep underground laboratories, in space-based observatories, and at particle accelerators, with WIMPs and axions remaining leading candidates, though no direct detection has yet been made. This enduring mystery underscores the need for new physics beyond our current standard model. Then, we explored the even more bewildering enigma of dark energy, the force responsible for the accelerating expansion of the universe. This astonishing discovery, made in the late 1990s through observations of distant Type Ia supernovae, completely overturned our understanding of cosmic evolution. Dark energy, comprising roughly 68% of the universe, acts as a pervasive, repulsive force, pushing galaxies apart at an ever-increasing rate. The leading explanation, Einstein's cosmological constant, presents a staggering theoretical challenge, with quantum predictions vastly exceeding observed values. Whether it's a constant vacuum energy or a dynamic field like quintessence, dark energy dictates the ultimate, chilling fate of our cosmos, a universe expanding forever into cold, dark emptiness. Together, dark matter and dark energy form the bedrock of our current cosmological model, Lambda CDM. This model, despite the unknown nature of its dominant components, brilliantly explains the cosmic microwave background, the formation of the cosmic web, and the large-scale distribution of galaxies. It is our most successful description of the universe, yet it is a description built upon a foundation of profound unknowns. The journey we've taken tonight is a journey into the heart of scientific inquiry, from initial anomaly to robust evidence, from theoretical speculation to precise cosmological models. It is a journey that reveals the universe to be far more mysterious and complex than our ancestors could ever have imagined, and indeed, more mysterious than we ourselves fully grasp even now. The fact that 95% of reality operates beyond our direct perception is a testament to the universe's boundless capacity for surprise, and a powerful reminder of the limits of our current knowledge. But in this vast unknown, the universe is not just what we see, it is also what we are striving to understand, the hidden forces and invisible substances that shape its destiny. We live in an extraordinary era, where the most fundamental questions about reality are not just philosophical musings, but active frontiers of scientific research. Massive telescopes are being built, detectors are growing more sensitive, and brilliant minds are tirelessly working to unravel these cosmic secrets. The missing universe forces us to embrace the unknown, to cultivate a sense of wonder and humility. It reminds us that our small planet, our bustling lives, and even our entire visible galaxy are but tiny islands in a vast, dark ocean. Yet, it also empowers us. We, small beings on a small world, possess the capacity to ask these monumental questions, to devise ingenious experiments, and to slowly, painstakingly, peel back the layers of cosmic mystery. We are the universe's way of knowing itself. And in seeking to understand the missing 95%, we are, in a very real sense, seeking to understand ourselves and our place in the grand, unseen scheme of things. So, the next time you look up at the night sky, remember what you've learned tonight. Those shimmering points of light, those distant galaxies, are not the whole story. They are merely the luminous signposts in a cosmos dominated by an invisible architecture, a universe largely missing from our direct view. And in that missingness lies the greatest adventure of all. Thank you for joining me on this journey through space and time. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, even though most of the universe is missing, the quest to find it is one of humanity's most profound and exciting endeavors. Good night, and may you never look at the universe the same way again.